And now it gives me great pleasure to introduce today's first speaker, Thomas Hubert, who is educated in Paris and Stanford. He is actually currently working at Google DeepMind. He was quite essential in developing AlphaZero. You've all heard about that, you know, this kind of, which was for many people a kind of an aha moment of what AI could do. And also closely involved with AlphaProof, which is one of the exciting developments of applying AI to mathematics. So, Thomas, the floor is yours.
So first of all, thank you very much for inviting me. I'm really grateful to be here, and I apologize I couldn't make the whole workshop. I wish I could have been there, but we just had our second daughter with my wife 6 weeks ago, so I couldn't be absent too long. Thank you. Do I need to press the button for the screen? I think it's gonna work. So yeah, I'm gonna talk to you about AlphaProof. You may or may not have heard about it, but today kind of the title is From the Labs into Your Hands. And so sometimes I have to start by motivating kind of why doing mathematics at all, but I think with this audience I don't have to do that. But I still decided to talk a little bit about computer formalization, even though I recognize many people who are way more experts than me in that domain, because I've heard that there is also a lot of people who are not yet converted. So I wanted to talk a little bit about this. I think it will be a good context for what's going to come afterwards. So yeah, basically computer formalization of mathematics is a little bit like writing mathematics in code. And so, you know, this is what it could look like. You know, there is quite a few kind of languages that have done that, Isabelle, Coq, but the one that seems to be very popular at the moment is this language called Lean. So it's a programming language, it's a theorem prover, and interactive proof assistant. So actually prefer to show you exactly what it looks like. So this is kind of the statement and the proof that Euclid proposed about that there is an infinite number of primes. So here at the very top here, that's the theorem statement. And I'm sure that even for those of you who actually haven't heard about Lean before, you can actually read this because, you know, this is using kind of the characters that we are familiar with in the math world. And the proof is this bit, and maybe you can also guess what it's doing. I think, you know, like the first line at least is particularly evocative, especially if you know the proof. We consider n factorial plus 1 and the minimum factor of this thing. This is basically the main insight of that proof. So as you can see, in some sense, you know, it's a language-based, high-level syntax, kind of that tries to mirror normal mathematics. And so it's not at all like kind of first-order logic kind of programs that existed before where it was, you know, really unreadable. In this case, you know, you can really express, you have the tools to express what almost you would write on a paper, at least in for some cases. And there is this interactive part. So what is the interactive part is that when you start to write the proof, then the computer tells you, oh, here is what you have to prove and what you have proven already. It gives you kind of your state of the proof. So in this case, for instance, what do we know? We know that, you know, n is a natural number, p is a natural number that is defined as being the mean factor of n factorial plus 1, and kind of this little turnstile symbol says, you know, what do you have to prove? So you have to prove that there is a p bigger than n that is prime. Fine. And then, you know, you try to write the next line of the proof, and then this thing updates. Now you've managed to prove that, great result, you have managed to prove that n factorial plus 1 is not 1. And so now, you know, you have this new fact in your arsenal, and you can use it to actually prove that p itself is prime. Right? It's almost obvious that p is prime because it's a factor of n factorial plus 1, but of course if n factorial plus 1 equal 1, then that wouldn't have worked. So that's why you need to, you know, you need to write quite a lot of details. And then at the end, if you've done everything correctly, actually kind of Lean tells you, tada, you've won, there is no more goals to prove, and you've proved the theorem. So this is a little bit what Lean looked like. And on top of this, I think one of the big aspects of it is that it really has a vibrant open source community of mathematicians. I guess many of you are here. And it has been used to formalize really cutting edge mathematics. And really kind of that community is on a huge quest to, as I understand, to build the math library of the future. And so it's called MathLib. And it's built open source, mostly on the free time of mathematicians. I think recently there's been quite nice grants from Renaissance Philanthropy that is trying to kind of sponsor a little bit this effort, and that's great to see. And it has a few fundamental kind of things it's aiming for. It aims to be general and unified. And so unified, it means that you really try to find the one concept that can be used in many different places. I was quite surprised to learn this when I learned about this unification kind of goal. I thought mathematics was already like that, but I've learned that a lot of concepts are maybe very similar but defined slightly differently in different papers, so that they're not quite compatible. And I think there is a lot of effort to find kind of the one definition, maybe the more abstract definition that captures everything. A few months ago, at least, it was about 80% of the undergrad curriculum was covered, but most of the library is above undergraduate level, with kind of sometimes big holes in things that you think it should be there and is not there, and sometimes going pretty deep in certain areas. I think one particularity of MathLib is that all topics of mathematics, it's one monolithic library, so everything is kind of connected together, which is quite important to represent modern math. And so why doing this thing? Why writing kind of mathematics in a computer, in code? And I think one of the reasons is because it kind of unlocks potential enormous synergies. And so maybe the two aspects is that it's going to use like software stuff, and it comes with this thing of perfect verification. So when you write the proof of the for instance the infinitude of primes, at the end it tells you this is correct, and this is all checked by the computer. So you don't need someone else to check. And so that kind of brings kind of instant wins. Correctness concerns disappear. You can trust giant proofs, and proof checking can be completely delegated to the computer. And so I think even for kind of the day-to-day mathematician, when you are peer reviewing your colleague's paper, if you could just focus on the ideas rather than on the correctness, that would probably make a big difference. It might change a little bit how mathematics papers are written as well, if you could leverage that. And then I think, so these are instant wins, and I know that in many areas of math, kind of the concern of correctness is maybe not a big concern. I think other areas, it start to be a real concern. So depending on, probably how abstract is that domain, there is more or less of these concerns. But I think it also has a few other knock-on effects that are very, very interesting. And so one of my favorite one is actually a point that Terry Tao kind of has brought up at least 2 years ago, is that it has the potential to unlock massive collaboration. So he was explaining that only in math papers, there's very few authors that collaborate because you need to check everyone else's work. While here, if you can kind of, delegate that to a computer, in some sense it opens up the opportunity to do kind of collaborations with, I don't know, maybe thousands of people, right? And so kind of change a little bit how mathematics is done, and I think also kind of incorporate kind of amateurs, because like they can kind of interact with the system until they reach something that is verified, and then that's a valid contribution. I think it could be also very useful in terms of education, in a sense that because you have to write all the details, in some sense you can kind of, the reader can be at the level of detail that is appropriate for them. At least it happens many times to me too. I read this proof and someone says, well, this is trivial. I'm like, okay, not clear for me, but if all the details were there, and then I could, in these parts that I don't understand very well, could go deeper, that would be great. And then from, more like kind of a person that's been doing a lot of code, kind of, to this idea of bringing all the tools of software engineering for math is at least, I think, from people who are like kind of coder, it feels like kind of a huge win. Like software engineers have been able to work together collaboratively on huge projects. And I think, like, for instance, the Mathlib projects already kind of leverages quite a lot of those tools, like from even the simple things like GitHub and kind of coordinating work together. And the last one is probably one that you don't think it's such a great thing. I don't know. It transforms mathematics into a video game. I think maybe you'd be happier if it was into just a game, but the reality is that, well, it's kind of a video game now that it's in Lean. And I want to illustrate this a little bit with just an anecdotal thing, where, something I tried myself that I felt like was really kind of a good illustration of this. So at some point, we were doing something with Alex Kontorovich, and we were doing something together, but we ran out of time. And so I said, oh, Alex, I would be really keen to try to finish this proof with you. But he was giving a conference, and so he was not available. So I thought, actually, maybe I can do it myself. And so I went into his project. I found the proof of the thing we wanted to prove in natural language, and I started to translate it in Lean. So in Lean, it's not that hard to state what you want to prove, and it's much harder to prove it in some sense. And so, but in some sense, you can kind of decompose the problem into simple things you want to prove. And then what was, I wouldn't know how to prove those things myself, but fortunately I had access to AlphaProof, and so I delegated all the tedious steps to AlphaProof and finished kind of all these things, and I was able to actually finish that whole proof. And on top of that, I actually found an error in the informal proof. It's a really minor error, like a sign, wrong sign things, but I wouldn't have felt comfortable saying, oh, like there's maybe an error here, Alex. But with the backing of Lean, then I was like 100% certain that, well, okay, like this sign was flipped. It's really a minor error. It doesn't change at all the argument, etc. But I feel like that shows that even for someone who is not a professional mathematician, I can kind of contribute to this project. I'm starting in the middle of the project. I have like kind of no context of what the rest of the project is, but I was able to do something. So I think it's kind of, it's anecdotal, but it's kind of a sign that these things are not completely a dream. There is also quite a few, challenges for computer formalization. So, it's still a very small community of mathematicians who have adopted Lean. And maybe one of the main reasons is it's like any programming language, it's still quite a steep learning curve, so you need to make a significant time investment. The library Mathlib is growing, and it covers more and more areas of mathematics, but there are also a lot of areas that are not covered, and you wouldn't even be able to state the problem you are working on. Like the tooling also is improving, and maybe I will show you maybe one of those tools that I hope kind of will help both in kind of making the learning curve kind of more accessible, a smaller barrier to entry, and maybe because of all of that there is a perceived lack of necessity for research. But to summarize, I think there is a huge enthusiasm from a really vibrant community. They are building the library of the future. That's a really, really super quest. I think it has really many ways in which it can unlock enormous synergies. And of course, there is still a lot of work to do and a lot of things to do. But I share the belief with this community that computer formalization will play an integral role in the future of mathematics. So that's for computer formalization. Now I jump into the lab. I jump into this thing that is called reinforcement learning. So it's like a total shift now. So now we're talking about kind of one AI technique. So this reinforcement learning is a very general framework of an agent that interacts with an environment and tries to achieve a goal. So if you are in that framework, it's a very general framework. If you want to do something but you don't have any goals, then it's not such a great framework for that. And in some sense, the easiest way to explain RL, so reinforcement learning, is just that it's trial and error learning. And really, the key is about interaction with the environment. And it's called to maximize the reward. There is always this notion of reward in reinforcement learning. and it's often kind of misunderstood that the reward has to be really guide you towards the solution, but it can just really kind of encapsulate a goal. So the reward can be 0 all the time until you reach the goal, you get 1. All right, and kind of this kind of framework has at least, that this is the stuff that has been done at DeepMind, but has kind of, is almost like a proven recipe, at least in certain domains, to reach kind of super intelligence. And so, it was demonstrated, the initial big results was in these video games called Atari, where you could have a machine that learns to play those video games completely on its own by just starting to play randomly and learning some patterns and then continuing to do that. And then I guess there was a big result with AlphaGo, where such a system was able to learn Go and actually defeat the world champion. And there was a bunch of subsequent things. And you can see here is a lot of domains are kind of games-like domains. But it was also used in AlphaDev and AlphaTensor to find kind of better algorithms, faster algorithms, and even in kind of in fusion to control kind of the plasma inside of a tokamak to try to, where the goal is to try to extract more energy out of the fusion reactor. So in some sense, really general framework. I personally had a chance to work on what I call the zero series. The zero series starts with something that was not zero. This is the AlphaGo. But yes. So, okay, what is kind of the zero philosophy? It's almost like a philosophy of research. But basically, it's all about trying to discover and learn new knowledge. The constraints you put yourself to start with is you start where you give no information to the agent. So it was applied. We did it first for Go and for chess, and so you would not tell anything the agent about Go, no techniques, no handcrafted features, nothing about chess, whether there is a pawn and a rook, and was these many points. No, we get rid of all of this, and we just try to learn by interacting with the game of Go and the game of chess, mostly here just playing games and trying to discover and learn new knowledge by yourself. And if you really started from 0, and then you can reach, I guess in those cases we reach really superhuman performance, then almost by construction, you can show that you've managed to discover and learn new knowledge. In some sense, if you've inputted 0 information at the beginning, it also means that you have a fairly general algorithm, which might be quite good for science, because especially in domains where many times when you want to advance science, it's like maybe we can advance it because these are domains that we don't understand very well yet, and so there is not that much data, and we need to kind of do experiments and learn about the domain we're trying to do and learn from that. And kind of maybe the last point is that paradoxically, if you can start from 0 and go to 1, then we could go from 1 to 2, 2 to 3, etc., maybe all the way. So that's the zero philosophy. So there are like 2 big results. Was basically that philosophy applied to Go and chess, and those systems learn by playing games against themselves, starting completely from random play. So this plot here is showing in the y-axis kind of the strengths of the Go player in a metric that's called the ELO, that is very useful in those games of 2-player games. And in the x-axis is how much time was spent on training the agent. And you have basically 3 curves. So the dashed horizontal curve is basically the strength of the program that played against Lee Sedol. So maybe kind of world champion level kind of level is just under 4,000 ELOs in this thing. And then they have 2 ways of training it. One is called supervised learning. So that's where basically we try to find all the Go games we could find that were played by humans. And we basically taught the neural network to imitate the games that were played by the human. And you can see that within an hour it gets really, really strong. And then after that it tries to extract more and more information out of those kind of games. But at some point it has kind of extracted all the information that was there, and kind of you reached kind of the strengths that kind of is expressed in this data, and there is not much more you can do. While in reinforcement learning is quite different. You inject, at least in that particular case, you inject 0 data and just generates its own data. And so in that sense, it's not limited by kind of the origin, what humans have discovered. And so of course, it's a terrible idea to use reinforcement learning if you are just going to do it for an hour. But if you have enough compute, then potentially you can reach really superhuman performance. And so not only is it very strong, is actually, so we managed to analyze a little bit, what kind of things it has discovered while it was training. So it's quite easy to do this. You look at, for instance, human patterns, and you try to plot the frequency at which they appear in the games while training is happening. And so, for instance, this plot shows, there is a special sequence called, for instance, the Karokan defense, and that, like for the first 2 hours, it's not discovered, and around 2 hours, it's discovered, and it's played quite frequently in the games. And then at some point, it thinks that actually it's not that good, and it starts to go away. While, for instance, the Queen's Gambit is a bit the opposite. It's like, actually, this is quite nice, and it continues to play more and more. And so Go, which is a game that I know much better than chess, you had exactly similar patterns, but what was really cool is that it came up with new things that actually completely changed the game of Go. The move that it plays at move 5, which is kind of you first play in the 4 corners, and then fifth move was different from what humans were playing, and it was actually a move that humans thought was a bad move. So that was quite interesting. But then after that, everyone started to play that move to try to understand, what was behind that. So also talk very quickly about alpha tensor. So it's not only about board games. We could use this framework to also try to find kind of faster matrix multiplication algorithms, and you could try it on different shapes of matrix multiplication. Kind of what is quite interesting in this problem is that in some sense to multiply 2 by 2 matrices, everything was known and discovered by Strassen. That is. Found out that you didn't need 8 multiplications, you could do it in 7 multiplications, and that was actually optimal. But nothing was known beyond that for instance, multiplying 4 by 4 matrices. So that the only kind of optimal algorithm is to kind of do this 2 by 2 multiplication twice. And so with this thing, we found kind of many different ways to multiply kind of 4 by 4 matrices that are not like kind of operation squared. And you can find for different kind of matrix shapes, different ways you can and try to minimize the number of multiplication. And that's also here where we learn how to basically tackle huge action spaces, because this action space was something like 10 to the power 30, so for practical purposes, kind of infinite, and so we are able to start searching in those infinite practical purposes, infinite action spaces. And so if I try to kind of distill what I think are why those systems could reach a superhuman level, is really kind of taking this trial and error learning at scale. And so, it might not be easy to do that in every environment, especially, if to do trial and error, you have to interact with the real world. And the real world is, you cannot speed it up, you cannot run a million Earths at the same time. But in domains like games and that you can simulate, then you can really try to scale up this trial and error learning. The second important thing is to have grounded feedback signal, because if you try something and sometimes you say, yeah, 1 + 1 = 3, that's fine, then you are going to collapse, and so you need to have really grounded feedback signal. You shouldn't invent your own kind of reality. And the 2 other points that I think were important, at least in the AlphaZero series, is this notion of search and the notion of curriculum. So let me now try to connect these 2 things, and why we thought that formal mathematics was particularly adapted to the to the AlphaZero kind of paradigm and the RL paradigm. And this is kind of the napkin master plan. So Lean gives us basically an environment where we can explore mathematics completely in silico. So we can simulate mathematics. And so that's kind of incredible. And plus, it gives us perfect feedback for proving. So whenever we manage to prove something, it tells us, yes, this is correct. And when we are not yet done, it tells us, you're not yet done. This is not a valid proof. And so really, it gives us kind of the first 2 arguments, like the first 2 points of scale-up trial and error learning, and grounded feedback on mathematics. And then kind of the 2 is an outrageous extrapolation of the work we've done before. They said, okay, then, we can tend to a super theorem prover and discover new truths like we did in Go, chess, and math. But at least, this is kind of the research direction, the question we are asking ourselves, given that it works so well in Go and chess, what can it do in mathematics? So yeah, you know, we kind of ticked the 3 out of 4 kind of important things from the get-go. You know, trial and error learning, grounded feedback that comes from the existence of Lean and the ability to be able to simulate mathematics. The search, we can reuse what worked well for us in Go and chess. And really now there is the only question that is left is this curriculum question. So, you know, in Go and chess, we had the perfect curriculum because we could play against someone of the same strengths as us. So if you, for instance, you know, if you play always against Magnus Carlsen and he just plays full strengths all the time and just crushes you at move 20 every time, it will be very hard for you to learn anything about kind of how to improve at chess, right? But if you are playing against someone who is roughly the same strengths as you, sometimes you win, sometimes you lose. And from that experience, you know, you can learn maybe, this was not the right move, right? And you can learn from that. So it's important to kind of have, in some sense, an opponent that is kind of roughly at your strength so that you can discover, you know, you can test your capabilities. And so in mathematics, you know, kind of the opponent of a prover is a problem. And so we really, to make this work, we need to, you know, in fact, you know, like maybe one of the problems different from Go is that, you know, it's not like kind of all mathematical problems come from one problem and then you can generate them all from that kind of universal problem. There is just a bunch of problems everywhere. And so really kind of to make this work, if you assume that RL is going to work, you need to generate high enough quality and quantity of problems. All right, so where do the problems come from? I think they come from 2 sources. Importantly, I think they really have to come from human mathematics because we really, kind of our goal is to really contribute to human mathematics. It's not to do alien mathematics. I think like, you know, like no one would look at it. That would probably be quite useless. And so really, you know, you want to be grounded in human mathematics. And the more pragmatic reason is that humans have already come up with a lot of interesting problems. So we should try to look at those. Then, of course, you know, if you want to have something that is also, you know, that leverage to the maximum kind of the properties of machines, you may want to also have your system kind of conjecture problems and think about problems just like regular mathematicians do, right? So, you know, it can be around human mathematics, potentially, you know, it can be, you can go a little bit in something that is a bit different if it helps, you know, human mathematics. So just to recapitulate this part of RL meeting formal math is in some sense, you know, we saw that we feel like we have a proven recipe to be an agent that can discover knowledge and potentially reach superhuman intelligence. At least we've demonstrated that in certain kind of well-defined tasks. The key ingredients are scaled-up trial and error and grounded feedback. In some sense, like formal math falls quite nicely into that kind of, into those requirements. All right, I'm going to go quickly over kind of, so, you know, fine, these are like the big ideas. So we tried it. And so kind of we had maybe our initial big results last year at the IMO last year. We tried it out. We run this at scale. We train our models with the grounded feedback that Lean gives us. And we really wanted to try it out in this at the Math Olympiads last year. And so I'm going to skip a lot of, you know, like the details. But one way to understand what we were trying to do is more like kind of an Apollo program. It's like, can we actually reach the moon? We knew that it was going to be hard to do it with I don't know how much watts does the brain consume, very little, with kind of the same time as humans and the same kind of energy demand of the brain. But we wanted to see if we could, you know, did we kind of start to touch the level of these kind of things if we have enough compute and enough time? Can we solve any of those problems? And so the final results we had is that actually our system was able to solve P1, P2, and P6. So there are 6 problems at the IMO. And we are partnering with another system that was developed at Google that was called AlphaGeometry, that's specifically good for geometry problems in the IMO. And so if you totaled kind of the score, we got basically 28 points, which was kind of in the threshold for a silver medalist. We just missed kind of the gold threshold by 1 point. And of course, kind of the caveat is that we use way more time and compute than humans. So, it's not necessarily to be compared with kind of the humans, but it's kind of one way to see it. Yeah, we were able, in partnership with alpha geometry, to solve 4 out of 6 problems. There were quite a few challenges. Like the challenges we saw was, there was gaps in this kind of math library, even for high school kind of problems, most notably in geometry, and that's why we kind of partner with this other system, called alpha geometry. The combinatorics problem were really difficult. It's actually the 2 problems we couldn't solve are combinatorics problems. One of the problems, I think we didn't even manage to formalize it because a lot of the tools were missing to formalize it. And in the end, we didn't make any progress on both the P3 and the P5 problems. And of course, I want to say it again, but we use many orders of magnitude more compute than human contestants. But from our perspective, we kind of successfully landed on the moon. But it's not something that I can give you in your hands, right? Because it's kind of a one-off. It's kind of a one-off. So, okay, what's really next for AlphaProof, right? Like, I think the IMO was a really great goal. It was a really an awesome goal when we couldn't do anything. But the goal was always to see, what can it do for, I don't know if that's the right term, but for real mathematics, for research mathematics. And kind of the steps are fairly clear. You really want to broaden kind of the knowledge that AlphaProof understands from high school to kind of more what exists in research mathematics. We really want to contribute to the frontiers of research math and make AlphaProof a useful tool that mathematicians can use, but also amateurs can use, or maybe people who it's not their profession to do mathematics, that bring them kind of the power of being able to prove things and kind of create eternal truths. And so, in that direction, so we've done a few things that you might have seen. So we started this repository that is open source. It's called Formal Conjectures, and where we invite the community to try to contribute to it. And so at the moment, you can see it has a bunch of research problems. Some so the majority of them are open problems. But there is also problems that have been solved, there is a paper and it's been solved by humans. A lot of them come from number theory and combinatorics that are, I guess, easier to formalize in Lean. And it also contains like very famous problems. But in some sense, we'd also very much welcome kind of day-to-day problems that, would be interesting. There is, I want to thank all the people who are contributing to it. There is about 39 contributors and 29 people who are actually returning contributors. And we've observed that as well, that for some people, that's their entry point to Lean. That's the first time they make a contribution to Lean. And so that's the graph of how many files are there in that kind of repository. And so the goals of this thing, I think it, like there is kind of a goal from the last point to serve as a benchmark for AI, but I think that this thing has a chance to be also something for the really good for the mathematics community. In some sense, it could be one place with an ever-growing list of formalized problems. So standard formulation, like standardized formulation of a problem, and because of that, there are many opportunities for corrections. In some sense, like it could be that the formalized statement is slightly wrong, but sometimes it's not only that. Sometimes the informal statement, the natural language statement, is also imprecise, and some kind of trying to really formalize that, is crystallize exactly what the problem is quite interesting. And so, for instance, one of the other hope is that it can also be a driver to try to expand math. So, as an example, this is like a big source of problems that are going into this formal conjecture dataset, come from this wonderful website that is from Thomas Bloom. It's called theadorschproblems.com. And so this is one such problem that was there back then. It's a problem that was solved, as you can see, and the comment was, it's a question, and the answer is yes, and it was shown in this paper. And so back then we had formalized this thing, and so we ran AlphaProof on it. And it came out, it says, this is, the answer is no. And we thought of, well, we must have made a mistake in the formalization, and we looked it up, but in fact, it turned out that really the answer is no, but it was more like a reporting error. That paper there in the Baumgartner paper had reported that the answer is no, and there was a mistake in the reporting. But what was maybe quite interesting afterwards is that kind of the proof that AlphaProof has found was different from the one that was in the paper. In particular, in the proof in the paper is more like the construction is about maybe invoking kind of almost the axiom of choice, while here AlphaProof came up with an explicit construction. So that was quite interesting, and so there is like this problems are being formalized. We try AlphaProof on them. Sometimes we disprove them. Sometimes it's an error in the formalization. Sometimes there is some bits and pieces missing in the informal statement, and so I think there is opportunities for this thing to become a higher and higher quality over time. So really, our hope is that this initiative will serve as a seed for a much richer data set of formalized conjectures. Potentially serving as a reference library for mathematicians, not only for formal mathematicians, but also for people who haven't been convinced yet. All right, now I just do I still have time? Yes, I have a bit of time. I'm not sure. I can't remember until when I had. Yeah. I want to do a little live demo of what it looks like to play with AlphaProof. And so we are really working hard to try to actually, make this available to all academics for free. And then, like you could, just interact the way I'm going to show you now. And so I maybe make it slightly bigger. Recently, basically, we were invited to the IAS by Akshay. And over there, I met Alex Kantorovich, with whom I played a little bit with AlphaProof, and he was actually very impressed by it. And so we had a very positive kind of work session together, and I came back very enthusiastic. But I thought, okay, that's only one person. We should try it with more people to see if that's a reproducible kind of experiment. And so shortly after the Big Proof conference, we invited 6 mathematicians to come and play a little bit with AlphaProof. And so there are some parts that were very successful. Some parts we discovered we had a bunch of bugs that we needed to fix. Some things where it's not yet super strong. But these are examples that we did with Bhavik Mehta. And so especially in that he was giving a talk in that conference about formalizing kind of combinatorics results. And at some point he mentioned that like he was formalizing something, and he realized there was this technical lemma that was really not interesting to him, but it actually took him something like 30 minutes to formalize. And then he realized there was another one, and another one, and another one. I think he said that there was about 30 of those. And so when he came to the office, I thought this is maybe a perfect example of something that would be really useful. And so I asked Bhavik to give me some of those. And so we tried AlphaProof on those. Let's try. So before that, let me try just, I use now the infinitude of primes to just see that kind of the system is alive, to see if it works. But basically the way it works is that you can sorry in lean means that well, you still have something to prove here, but you say, oh sorry, I will do it later. And so we can kind of call AlphaProof on those sorry bits, the bits that we haven't proven yet, and then hopefully it will return with a proof. So let's see. So this is my little test whether to see if the system is alive behind the scenes. I hope so. I think the first time it takes a bit of time. It's always the stressing moment where nothing happens. You're waiting. Maybe in the meantime, let me describe a little bit kind of those technical lemmas. There is actually, I don't think it's very interesting to understand exactly what are those, but you can see, it's about kind of bounding kind of stuff with with logs and kind of 1 over log of something, some factors, etc. Some really technical lemmas that appear in the formalization of those problems that are, not really interesting. Kind of the only thing you may not even care about the proof. Okay, so the system is alive. It came back with that bit of the proof. So let's try on this thing. So as you can see, so basically I'm going here and I say, okay, AlphaProof, go and try to prove this thing. And so I can send it on multiple things, and you will try to go and solve this kind of in parallel. And so you can even see by the names that Bavik gave to this lemma that are not very interesting. There's such a large n, wow, and now the last large n, oh, large helper, and then afterwards there is the last large n, but no, there is how large can we go, and yet another. Okay, so you've seen it's starting to come back with some of the proofs. So it inserts them here, and then kind of lean goes and checks the proof. Well, I guess it's checked on our side, but you really want to check it on your side. It's being checked, and kind of the proofs are inserted, and then so our experiments with Bavik was that we run those those technical lemmas, and then AlphaProof could really do it in a matter of minutes, like 2 minutes per lemma. You could run them in parallel. And so if he had like 30 lemmas that took him 30 minutes each time, we basically saved him 14 hours and 55 minutes or something like this. And so, I think that's kind of a great example where potentially these are things that, you don't really care that much about what exactly the proof looks like, and you just want to know that it's true and kind of move on to the things that is really interesting to you. All right. And so we tried another kind of, so you see, you can kind of get a lot of things fairly quickly. So maybe that's one point I wanted to communicate. Well, to solve the IMO problems last year in July, it took, it took more than. So we report that it took 3 days. So here, luckily, we don't have to wait 3 days for these to come back. It actually is coming back in a matter of a few minutes, and I hope these kind of things could be useful. I think it would have been useful for Bavik at the time. Another thing that Bavik tried that he found that was maybe the most impressive thing that he tried was to try to prove this Fisher inequality. So I think that's a result in combinatorics as well. So let me launch it. That takes usually a bit more time, and so I'm sure that I'm not the best person to explain kind of this lemma, but what is interesting in this lemma is that I guess it's a theorem about finite sets, but the way you are going to prove that result is by going into linear algebra, and actually, so we launched that, and in the proof that AlphaProof returned, you could see that it really it went through this linear algebra. It did the same construction of the kind of the vectors you have to consider, and kind of could do all of this autonomously again in a couple of minutes. So yeah, hopefully it will work now. That's the last thing I wanted to show you. So yeah, I'm happy to take questions in the meantime, if anyone has some questions.
Okay, let's start thinking. So while AlphaProof is thinking, already is here. So we have a few minutes for, I would say, a few kind of technical questions, or not technical questions triggered by this presentation, and we'll have ample time to have a more broader discussion. But some questions, yes. I don't think I want to go around with Mike, so perhaps just stand up, yes, a shout.
So I don't know if it would be possible to look at slide 22 in your presentation again. There was a picture there with your reinforcement learning, and I was surprised that it tapered off. I mean, began to taper off at the expert system level, the reinforcement level.
Here?
And then it jumped. I don't know if you had an idea.
Yeah, so these jumps are like kind of so okay, I can explain technically what happens. Is that it used to be that what you would do is, like when you optimize those systems by gradient descent, you have something you called a learning scale, and that it turned like kind of the technique that was used at that time is that sometimes you would drop that learning rate, and so it would kind of go and move in the scope, and then you drop the learning rate and it starts to go down kind of, and so that's kind of, you see it in the supervised learning as well, like kind of these jumps. These was the techniques that were used back then that is not used anymore. It came up with some more intelligent optimizer.
I was just surprised that its initial tapering off was also at the human and expert system level. Imagine it could have been 1,000 ELOs below.
Yeah, I think that's more, I wouldn't interpret too much on that. I think it's maybe more kind of the optimization, the human optimization of, like when to drop that learning rate. Like it could have dropped it earlier and then, like, yeah, I wouldn't read too much
Does the
into
curve
that.
reach an asymptotic?
In Go, we had this thing where we run what we call the AlphaGo master thing. It was in between AlphaGo and AlphaGo 0. And that thing ran for 40 days and was continuously getting better. But it's a property of the environment a little bit, because in Go you can always improve by half a point, by a point. And so there's always one player that wins. Where in chess at some point, in chess we saw that the curve was plateauing, because basically Alpha 0 against Alpha 0, they were drawing all the time. Yeah. So I think that's a property of the environment a little bit. In Go you can continuously kind of get a little bit better.
I thought there was a question here in front. Yeah, you. Just speak up.
Are there plans for a public release of any of this?
Yes, so the tool, we are really working really hard to make it available. So, it will be first with a small group of people to just find the corner cases and see where it works, and kind of how can we improve that thing. What I showed you today is, in some sense, is our first initial guess of what could be interesting, but we want to build that with this community and see, what would actually be very useful. I'm sure that something that could take some natural language and actually write for you maybe what the lean is would be very interesting, and so we can build that all in together. But I really expect that the tool would, the first people who can use the tool would be in a matter of, this year. Yes, definitely.
Yes.
I'm curious, like, what is the technology behind this? Is it just large language models, or like in alpha geometry also have some kind of classical reasoning engine?
So it's you can really imagine that it's like it's really like Alpha 0, but where the neural network is a neural network that can understand the language. So it's like a small, it's like a large language model, but it's not that large. Yes, it's a language model, let's say, but that's kind of technology.
Yes, in the very back. Speak up.
So the tool sounds really amazing, and I look forward to playing with it, but I'm a bit intrigued by your remark that you would offer it for free, because obviously you have invested quite a lot of time and money into this. So how do you see this in the long run?
Yeah, well, so I guess it's true that, if suddenly 1 billion people were using AlphaProof, then that would potentially be a problem. I know that we are not yet there. So, you have, it's true, you have Google, and, you have Google as a big corporation. Inside of that, we have like Google DeepMind, and inside of Google DeepMind, there is something called the science unit. And the science unit's goal is to just advance science. And so we are part of that unit, where our goal is to, contribute to research maths, kind of do science, but in the, I don't want to say the narrow field of maths, but kind of focused on maths. And just the same way as, like the image I have is just the same way as AlphaFold was given for free to fold protein. So that's kind of the image we have. Yes.
And AlphaFold, who got the Nobel Prize. Yes, in the back.
Have you tried combining this with symbolic AI, which is now conveniently available in Lean by Lean SMT and Lean Hammer?
Sorry, could you repeat?
Have you tried combining it or contrasting it with symbolic AI, which is now conveniently available by Lean SMT or Lean Hammer?
We haven't tried, but whatever kind of tactics is
Can
available.
you perhaps explain for everyone what the issue is?
I'm not exactly sure what the issue is, but if it's some kind of tactic, then that's something that AlphaProof can use. So whatever tactic or tools that kind of the community implements in Lean is potentially another tool that AlphaProof could use. And so maybe sometimes I imagine sometimes, like you are a problem, and it might be more efficient to use a SAT solver than to write a proof. And then I think that maybe that's linked to your remark. Then there is a tactic that basically calls a SAT solver, and then yes, like you could plug that in and try to use it.
Okay, so one more question, and then we go. Yes.
I'm just curious if you've seen kind of what kinds of proofs AlphaProof kind of struggles most on, if you've seen any patterns there.
So
Yeah, so the question was, are there some problems that are particularly difficult and AlphaProof struggles with?
yeah, I think it's so I guess in kind of the domain of research math, I'm sure it struggles on a lot of things, but we just haven't,
We all
I
struggle.
personally don't have the expertise to test it on all, so that's part of kind of what we also hope to discover with you. And of course, for the IMO, for instance, like the clear thing it was struggling on is combinatorics. It was clearly much stronger on number theory and algebra kind of things that are also, for instance, easier to auto-formalize than kind of combinatorics problems. So these are all related in some sense. Kind of the auto-formalization creates the problem that the RL can train on. But if your auto-formalization is not that good, then you are never generating kind of very interesting problems. And so you're never training on the very interesting problems. And maybe that feedback can also come back. So it's kind of a double circle. But in particular, IMO combinatorics were hard to formalize. We were much better at doing kind of algebra and number theory, which is almost the same in between LaTeX and Lean. So I'd imagine that these kind of things, and of course all the things where MathLib has a big gap on, that would be difficult for AlphaProof to work on them. Yeah.
Well, thank you very much. Let's thank Thomas for his presentation. We see him back.